In this video, we're going to look at how to use our knowledge of reading element data from the periodic table in order to construct Bohr diagrams that represent those atoms in a diagrammatic form. So the first information that we can get using our example element magnesium is the number of protons and electrons that magnesium has, which we can simply get by looking at our atomic number, which is 12. Next, we need to do a simple calculation to find the number of neutrons. We know that the number of neutrons is equal to the rounded version of our atomic mass minus the number of protons, because the number of protons plus the number of neutrons is equal to our atomic mass. Now, since the number of protons and neutrons can't have a decimal, we're going to round 24.31 down to the nearest whole number, which is 24. And if we take our atomic mass of 24 and subtract the number of protons, which is 12, we can determine that magnesium has 12 neutrons as well as 12 protons. Now that gives us all of the information that we need in order to write the nucleus structure in the Bohr diagram for magnesium. So we start with the element symbol because we need to know what our element is. So let's put Mg, the chemical symbol for magnesium, in the center. And inside the nucleus, because protons and neutrons are the subatomic particles that we find in the nucleus, we're going to indicate how many protons and how many neutrons magnesium has. So it has 12 of each, so what we can do is write 12p, and we remember that protons are positively charged, so usually we can indicate this with a positive sign here, indicating that because it has 12 protons, it has a nuclear charge of positive 12, and because neutrons don't have charge, all we need to indicate is 12n, and we don't need to write a charge here because neutrons have no charge. So the hardest part of writing a Bohr diagram is organizing the electrons. Now, I've listed out 3 different shells. Remember that each of these concentric circles outside of the nucleus represents a shell where electrons are stored, and each shell has a specific number and arrangement of electrons. For example, if we go to the innermost shell, the one closest to the nucleus, the innermost shell can only contain 2 electrons, and these electrons exist in a pair. So for reasons that we can't get into, electrons are always represented in pairs where that is possible. So the way that we would represent the 2 electrons in the innermost shell is we would write 1 electron like this and a second electron like this so that they form a pair. Now, when drawing Bohr diagrams, it helps to keep track of the total number of electrons we've used. So magnesium has 12 electrons, and we just used 2 in the innermost shell, meaning that we have 10 to go. Now, each of the second and third shells, the ones outside of the innermost shell, can contain 8 electrons that form into 4 pairs. Now, the way that we write electrons in the second and thirdmost shell is that before electrons can form a pair, we usually put 1 electron in each direction. So 1 in the north, 1 in the east, 1 in the south, and 1 in the west. Now, if we've added 4 electrons that don't exist in pairs, we know that magnesium has more than 8 electrons here because it has 12 electrons in total. Now, after we've added these first 4, we would add the second 4, 1 in the north, 1 in the east, 1 in the south, and 1 in the west, like this, to show that we have 8 electrons that exist in 4 separate pairs like this. So if we keep count of our electrons, we just added 8, meaning that we have 2 electrons that need to be added in. So now it's time to put these into the valence shell. So again, 1 in the north and one in the east, and we can't pair these because in order to pair them, we need to have added 4 electrons, one in each direction first. So this means that magnesium has in its valence shell, remember that's what we call the outermost layer, it has 1, 2 unpaired electrons like this. And in short, that's the process of drawing a Bohr diagram. Start with the nucleus by listing the element symbol, the number of protons, and the number of neutrons, and add electrons to the appropriate shell, starting with 2 in the innermost shell, and then 8 in the next 2 shells that come. Now, in Science 10, you will not be required to draw Bohr diagrams that have more than 3 shells because the number of valence electrons becomes greater than 8 and the structure gets a little bit more complicated. However, we still need to talk about something that we call ions. So an ion is what happens when elements either gain or lose electrons, which means that these elements are now going to have charge. In fact, that's the definition of an ion. An ion is simply an atom that has charge. Now, this is where we're going to explain why elements form specific and regular charges. Now, the reason why ions form is that the number of electrons that they gain or lose is a specific number of electrons that causes their valence shell to become full. Now, most of the time, this means that the valence shell is going to have 8 electrons, and there are a few exceptions to this, namely hydrogen and helium. But we're going to take a look at one example of a situation where an element loses electrons and one example where an element gains electrons. So we can see that aluminum has a charge of positive 3 because aluminum has lost 3 electrons, and when aluminum does this, that makes aluminum what we call a cation. Cation meaning that it is a positively charged ion. Now, from oxygen, we see that its charge is negative 2, which means that oxygen has gained 2 electrons, and that makes oxygen as an ion an anion, meaning a negatively charged atom. So let's go ahead and draw the Bohr diagrams for each element, forgetting that it's an ion. So if we start with aluminum, we know that we're going to have 13 protons and electrons, and if we take aluminum's atomic mass and round it to the closest whole number, this would be 27, and 27 minus 13 is 14, so that means it's going to have 14 neutrons. So let's write the nucleus structure here. So aluminum with 13 protons that are positively charged and 14 neutrons. Then if we do the same thing with oxygen here, let's find the atomic mass of oxygen, which is 8. So that means oxygen is going to have 8 protons and 8 electrons, and oxygen's atomic mass is a nice round number, 16, and we know that 16 minus 8 is simply 8, which means it's going to have 8 neutrons. So let's put the chemical symbol here with 8 protons and 8 neutrons. Now, when it comes to adding electrons for each of them, aluminum has 13 electrons, so let's put the first 2 in here, 1, 2. 13 minus 2 is 11, so we have 11 electrons left. Then let's put the 8 in the second shell, 1, 2, 3, 4, 1 in north, south, east, and west. Then we can start to pair them like this, 1 in north, south, east, and west, so that we have 4 pairs. So 11 minus 8 means that we have 3 electrons remaining. So 1, 2, 3, and there is the structure of neutral aluminum. Now, if we do this with oxygen, again, oxygen has 8 electrons, so what we can do, let's put our 2 electrons in the innermost shell. So 8 minus 2, meaning that we have 6 electrons here. So 6 is not enough for a full second shell. So that means we need to do 1, 2, 3, 4 before we can start to pair, and then the last two, 1, 2, means that oxygen now has 2 pairs of electrons in its outermost shell with 2 that are unpaired. Now, remember that the goal of an ion is to get a full valence shell, which usually means 8 electrons. Now, for aluminum, which is easier for it to do? Aluminum has 3 valence electrons, which means it can either get to 8 by adding 5 electrons to its outer shell, or it can take the 3 electrons in its valence shell and lose them. So which sounds easier, gaining 5 or losing 3? Well, 3 is a smaller number than 5, so aluminum is going to lose its 3 valence electrons in the outermost shell. So if we simply erase those, now we have the ion form of aluminum, because we can see that it has lost its 3 electrons in the outer shell, so the second from outermost shell in here has a full 8 valence electrons, and this is what aluminum looks like as an ion, which we would write as Al3+. Now with oxygen, we see that oxygen's outer shell has 6 valence electrons, but it needs 8, which means that oxygen can do what aluminum does and lose the 6 electrons in its outermost shell, or we can simply take 2 electrons and add them in to its outermost shell. So which sounds easier for oxygen, gaining 2 or losing 6? Well, 2 is a smaller number than 6, so that sounds easier for it to do. So what this means, if oxygen takes 2 electrons from another element like this, we can give it a full valence shell, and because it's gained 2 electrons, we would write it as O with a -2 charge. This concludes our instruction when it comes to drawing the atomic structure of each atom in the form of Bohr diagrams. To test your knowledge and to see whether this makes sense, you can take a look at this thinking question here, which gives you an idea about why certain elements are reactive based on their gaining or losing of electrons. But for the beginning, start by trying to identify the number of protons, neutrons, and electrons that each element has, and see if you can put your knowledge of drawing Bohr diagrams in order to construct the atomic structures of each of the elements in the practice problems here.